Consider the objective function of f that should be maximized of the variables x and y. In this case, it is a quadratic function. Its objective space can easily be visualized by the following graph. And it is clear to see that the maximum would be probably here on the top. Other techniques can also be used to optimize or maximize these continuous objective functions. For example, differentiation, and then setting the derivative to 0. This will then yield the optimal solution of x and y equals 0 and 0. For the vehicle routing problem, as many of you know, where there's a depot and various customers, and then vehicles need to be routed between these customers, it is a discrete problem in nature, and therefore its objective function cannot easily be differentiated, or such easy techniques and creative techniques needs to be used. This is an example of how such an objective function would look like. It should be minimized, which is a function of the binary variables x. It is the sum of the multiplication of x, which is the binary variable if a route is established between customer I and j, multiplied by the cost if such a route between I and j is involved. The urban transit routing problem does derive from the popular vehicle routing problem. And in this case, the encircled numbers represent bus stops, and the colored lines, the red and the blue, represents bus routes on which buses traverse and transfer passengers from their origins to their destinations, setting up a route network. The black lines represent the road network infrastructure that is available to the buses. It is also a discrete problem in nature, and therefore no simple easy techniques exist that we currently know of that can just optimize or solve this problem to optimality. It is usually solved in the context of two objective functions, the first being the average travel time for passengers, and here the cost, denoted by d, is the distance between customer I and j, is multiplied by the shortest time traveled. Sorry, the d is the demand, the a is the shortest time traveled between vertex I to vertex j for each passenger for a given route set r, the route set r being the red and the blue routes. It is then divided by the denominator, which is the sum of all the passengers or demand in this context. This gives the average travel time, measured in minutes. The second objective function is then the sum of all the edges of the bus routes. For example, all the weights on the network for the route set R. For the agenda for today, a bit of a deeper dive will be taken into the urban transit routing problem. Some mutations that were employed will then be made mention of that were incorporated into solving of this problem with a non-dominated genetic algorithm 2 approach. Thereafter, a dynamic mutation strategy is introduced that helps to manage all of the mutations that were incorporated into the genetic algorithm. Some results will be taken a look at, and finally, we conclude with a summary. So the urban transit routing problem is a notoriously difficult to solve optimization problem due to its discrete nature. Furthermore, it contains inherent complexities due to the interrelationship of its decision variables, namely the bus routes. Further complexities involve the modeling of people in choosing their itinerary for reaching their destination. The distribution space is enormous, and creative techniques are required to find high-quality solutions in the difficult to navigate objective space. Here we have a popular benchmark instance called Mundell-6, which various researchers have used to validate their algorithmic approaches. It consists of 15 vertices or bus stops and 21 edges, an associated distance matrix and origin-destination demand matrix. The urban transit routing problem can be cast as an integer programming problem, which has two conflicting objectives. The first being the average travel time or passenger cost measured in minutes, and also total route time or operator cost measured in minutes. These are the two objective functions that have been seen in the introduction. In terms of constraints imposed on this problem, it should be required that no more than a specified number of routes be allowed for each route. Also, the trip time per route should be between an upper and a lower bound. It is required that the bus route network be connected so passengers will be able to get to all their destinations using the transit route network from their origins. And also no cycles or backtracks are allowed in any of the routes. So back to our test case instance. Here's an example of how a feasible solution would look like in the decision space. On the left, we have the total route time being the one objective and the average travel time being the other objective, both measured in minutes, being 87 and 19.69 respectively in this case. Below here, we have the decision variables. It is a list of lists, with each list then containing the sequence of the bus stops that in the order that they should be visited by the buses. And it is represented here visually with different colored lines. So with regards to the solution implementation employed to solving this problem, a non-dominated sorting genetic algorithm 2, or NSGA2, solution implementation was applied to solve the model for the open transit routing problem. Crossover was applied between two route sets in order to create one offspring solution based on routes from its parents. Furthermore, various mutation operators were incorporated that may be applied to alter solutions. And then finally, a dynamic mutation strategy was followed by altering the mutation ratios during the search based on the performance in the previous generation. Here's an example of the non-dominated attainment front that would be obtained by using such as an NSGA2 solution implementation. On the horizontal axis, we have the average travel time measured in minutes, and on the vertical axis, we have the total route time, also measured in minutes, being the two objectives considered in this problem. And this is then compared to two benchmark results from people in the literature, from researchers there. And we can see here that the NSGA2 does perform on par and even outperforming some of the solutions found in the literature for this small test case. Let's take a deeper look at solution C, which is here found in objective space in the context of decision space. Here we can see in the visualization that many routes are directly linked to other bus stops, therefore meaning passengers will have direct access to their destinations and therefore would incur lower travel time costs. On the other hand, if we look at solution D, which has got the lowest total route time and the longest average travel time from the non-dominated set, we can see that these routes are quite densely populated, or sparsely, populated. And this means that passengers would have to incur multiple transfers to get to the destinations, therefore incurring transit penalties and then having a larger average travel time on the overall network. So with regards to the mutations that were employed in this study, these were mutations that are found in the literature, and the best of those were adopted into the solution approach. First, we have extend, where a vertex is added to a route randomly. Also, we have the reduce mutation, where a vertex is randomly removed from a route. We also have the add inside, which adds a vertex inside a route randomly, but it should be feasible, of course. And then delete inside removes a vertex from the inside of a route. We have the inversion of vertices of a route. A vertex may also be relocated within a route. Some vertices may be replaced within a route. And between routes, a vertex can also be donated from one route to the other. Vertices may also be swapped between routes. And finally, routes may be exchanged by exchanging segments from a common vertex with the segment of the other route. Furthermore, a set of new mutations were introduced into the study as from the creation of this project. The first is cost-based extend. This stochastically adds a vertex to a route that is proportional to the demand that it would satisfy given the route set R. And cost-based reduce stochastically removes a vertex from a route with the probability that is proportional to the demand that it would not satisfy anymore when removed. The dynamic mutation strategy that was adopted follows the notion of a hyperbeuristic approach. So a hyperbeuristic is basically a heuristic for finding other heuristics or using other heuristics, but more formally stated, a hyperbeuristic is search methods or learning mechanisms for the selection or generation of heuristics for solving computational search problems. The amalgam concept introduced by Vrucht and Robinson was utilized in this designing this approach, but the basic notion of amalgam is it is a selective hyperbeuristic with a perturbative nature. It is utilized in evolutionary algorithms for deciding upon various sub-algorithms to be performed on subsets of the population of candidate solutions for each generation. The selection is governed by affording more computational resources to sub-algorithms that were successful in previous generations, and then affording less computational resources for sub-algorithms that performed poorly in the previous generations. So with regards to the approach adopted, a dynamic mutation strategy based on the amalgam concept is that instead of sub-algorithms, the amalgam selection method is applied to mutations instead. The selection process governs the number of mutations to be applied to the following population. This allows for a more flexible approach towards solving computational search problems, as the algorithm adapts the mutation usages for the specific instance at hand at the current search time step. So getting to some results, I will first visualize how 5 of these popular benchmark instances look like. The first being the Mundell 6 instance, as you have already seen, having 15 bus stops. The Mumford 0 instance has 30 bus stops. The Mumford 1 instance have 70 bus stops. Mumford 2 contains 110 bus stops. And then Mumford 3, the largest of all the instances currently, has got 130 bus stops. The mutation ratios was then compared for each of these instances over 20 runs of an NSGA2 implementation. First, we have the legend of 10 mutations that were incorporated. These 10 were chosen empirically based on their performance. So for the Mundell 6, we can see the various mutation ratios over time. So the horizontal axis being the number of generations and the vertical axis being the mutation ratio for each of these mutation operators. It's interesting to note that over time, over generations, that the cost base reduced does increase in performance and more computational power is afforded to this algorithm due to its better performing, qualities. For the Mumford 0 instance, we can see a sort of a similar approach where the cost base reduce does gain more performance over time or does give better performance over time, but we can also see that the blue, red and yellow also gradually increases over time, where the orange, blue, pink and green in the middle does reduce over time, indicating that they're not performing as well as the other operators. Here we have Mumford 1, Mumford 2 and 3, and we can see sort of a similar approach being followed, or pattern being followed, but here on the 1 instance we have yellow, red and blue doing a bit better, and here the ratios do seem to change a little bit over time. Thereafter, a hypervolume comparison was conducted for each of these 5 benchmark instances, considering a dynamic approach, as mentioned previously, for managing the mutation strategies, and also a static approach, where all the mutation ratios were kept constant. Here we have the Mundell 6 instance, and this indicates that on average of the 20 runs, the static did perform better, but when merging these 20 non-dominated sets obtained, and getting the overall non-dominated set, the dynamic did prove better. For Mumford 0, we see that on average of the 20 runs, the dynamic proves better, but the static did perform better overall when merging these 20 runs as non-dominated sets and getting an overall non-dominated set. That is denoted by the top filled circle. And then for Mumford 1, we see that on average they're roughly the same, but the dynamic having a better overall performance. Here for Mumford 2, the dynamic does perform better overall, but on average, but overall the static does perform better. Then finally for Mumford 3, we have the dynamic performing, the static performing better on average for the 20 runs, but the overall performance does seem to be similar. So the conclusion drawn from these is it's not yet clear whether the dynamic mutation strategy is for certain better in the context of an NSGA2 implementation and in the context of an urban transit routing problem, problem approach. So let us take a look at the non-dominated sets obtained as compared to the results of the literature. Here we see for the smallest instance that the performance is once again on par, and it should be noted that the horizontal axis is the average travel time and the vertical axis is the total route time, both of them being the two objective functions considered in the study. And here the orange and the red solutions are other multi-objective approaches, while the other solutions on the extremal points were only single objective approaches. Here the blue and the green results, the blue being the dynamic attainment front and the green being the static attainment front. So for a smaller instance, it does seem that they do perform on par and even dominating some of the solutions at some areas. For the Mumford 0 instance, it is clear that the dynamic and static approach outperforms most of the results returned in the literature, and very similar non-dominated sets, but the dynamic does have a bit of a advantage here at the one extremal point. For Mumford 1, we see once again two very similar performances by the dynamic and static, with the dynamic also having some more solutions on the one extremal point. And for Mumford 2 instance, not dominating most of the results in the literature, we see that the quality of the non-dominated set is a bit better here for the dynamic attainment front than the static attainment front. Finally, for the largest instance, Mumford 3, we see once again two very similar non-dominated sets, but it does seem like the quality of the dynamic attainment front looks a little bit better than the static approach, and also they're not dominating most of the solutions in the literature. This approach of thinking of having dynamic mutation strategies can also be extended to other meteoristic classes. For example, a similar approach may be taken for a trajectory-based search. One such application in the context of dominance-based multi-objective simulated annealing, or the DBMOSA, is using a stochastic roulette wheel selection procedure for managing various perturbation ratios. The perturbation ratios are updated and based on the success of previous iteration, and a record is kept of each perturbation's performance. This equips the DBMOSA algorithm with a robust search mechanism, prioritizing perturbations that led to the inclusion of solutions into the non-dominated set. Here, the perturbation ratios will be showcast. So similar to the mutations, some perturbations were then adopted. And for the Mundell 6 instance, we see not a lot of changes. But as the problem instances increases from Mumford 0 to 3, we do see that more rapid changes are found, and especially the cost-based reduced and cost-based extend is given more prioritization. Thereafter, the hypervolume was then compared over 30 runs when considering mutation strategies for dynamic and a static approach. And here it is clear from all 5 instances except Mundell 6 that the dynamic did outperform the static in terms of hypervolume performance. So in conclusion, 2 new mutation operators were introduced, A method for managing numerous mutations was introduced based on the amalgam concept. A similar approach was adopted for a trajectory-based search based on the roulette wheel selection procedure. When applied to benchmark instances, high performance was evident. An evaluation was also then presented between dynamic and static mutation strategies. Insights was gained into how, in different instances, mutations were prioritized differently. And finally, a dynamic strategy for mutation and perturbation management may be beneficial for certain optimization problems with difficult objective spaces. Thank you.